Hello again, this is Mike Hicks back after a technological absence from Business Administration 602. And so, what I'm going to do is I'm adding this lecture just to sort of give you a review of where we are. And then in the next lecture, I'm going to cover the practice exam. And then hopefully that clears up the questions that many of you have had about what we're doing. And so I've had a few folks who said, "Gosh, I just don't really know where we're at right now." And I'm struggling a bit. So I thought this is going to be a pretty good way to fix that. So let me just go over it really quick. So far in this course, which the first half is statistics and the second half is primarily economics, and there's some blended portion in the middle, what we've explained is that data can help us understand the world. And there are, if your background is in a social science or if your background is in business, you have done that. If your background is in literature, you may not have, or there are some fields where you will not have spent time with quantitative or really qualitative data to inform what you're trying to do. And so in the business applications and in the social sciences, you're really going to use data to explain the world. To analyze that data, you really benefit from a couple of things. And the first one is having lots of observations. And that's not always possible. There are classes where we'll talk about small data problems and qualitative research. But in this class and in economics and the follow-on courses, we'll be talking about quantitative research. And in these cases, we're looking to have as much data as possible. When I was in your shoes as a young graduate student, this is just after the advent of ubiquitous desktop computers that were slow and had very little capacity. The number of data oftentimes used in models were reasonably small, anywhere from a few hundreds to a few thousand. In the last week, since I've been waiting for my microphone to come in, I've done some statistical models with 3 trillion calculations from a desktop at home over the internet. And so there's a very big explosion in this work, and these data sciencey type applications are increasingly important. The problem is the big data complicates the analysis. Acquiring the data is important, cleaning it is important, getting it in a usable format so you can do the arithmetic or mathematical calculations on it is a challenge, and then introducing it into software that makes that easy, coding the software where necessary is part of this problem. And you're going to learn some of that in later classes. In this class, I'm doing the most basic stuff. And in the first most basic data analysis, what we often care about is just comparing a single variable. We might take a person and we might compare that person to the characteristics of a group. So we say, we want to know if an individual is taller or shorter than average. And so maybe we'll have a sample of human beings that we can do to test that. We obviously aren't going to measure all 6 point something billion of us, so we'll get some subgroup. The discipline of how we understand what the subgroup is used for is often this a sampling or distribution theory. That's something you'll cover in later classes, particularly in marketing. And we'll just look at that person, compare them to that group, and we'll use some measure of difference to determine that. What's the mean size of the group? What's the standard deviation? We'll talk more about that in a minute. Or we want to compare two groups. So let's say in business, let's say we're doing quality control. Maybe we have measured the size of all, a sample of all the previous bolts that we're producing, and we're checking the quality of the threads for damage. Well, we open a new factory, what we may do is then want to compare those factories' quality measures of threads against the old factory to see if there's a difference. So that's comparing two groups on a single variable. We're comparing the old factory and the new factory, and we're just seeing whether or not that variable is, which is, let's say, whether or not they fit into a certain tolerance level of error. works, or we may have two groups of people who we think are otherwise identical, and we wish to see if they're on average taller or not. And in environments where we can craft an experiment, like in marketing environments, we may try to create a tool or control group and a test group. And in the control group and test group, if we can, we would like to make everybody identical. So let's say we wanted to evaluate an advertising campaign for hair loss products. We might find, 100 men who are experiencing hair loss, and a different 100 men who are experiencing hair loss. Same ethnic group, same relative age, same income, and then we'll show them two sets of advertisements, right? Or we'll show them different advertisements to see which one they respond to in different ways, and we can survey them or take their heart rate if you're excited about preventing your hair loss. Those are sorts of things that you might be able to do. More commonly, we don't have that luxury, so we can't create a natural experiment to do what we're trying to do. In this example, and almost every other example we have, the way we measure these things is through what's called a signal-to-noise ratio. And a lot of people in my discipline in economics or in business disciplines and statisticians in general may not use the term signal-to-noise ratio. That's used more often in the physical sciences, but it's the same idea that we have something we're measuring, the signal, and that signal could be the respondent's answer to a questionnaire. It could be our measuring their income. It could be their amount years of education that they have obtained or where they live. Those are all signals of something. And then the noise is the variation in the broader sample. So if we're trying to understand whether or not a person's above average in height, we have a height, but and you can't just pull one person out and compare them. That doesn't tell you anything other than one is shorter or taller than the other. You have to have some distribution or some noise around that. And the noise can come from two areas. It could be random noise because your measurement errors are off. You have somebody just out there measuring and they're making systematic errors, or it could be a characteristic that you miss. So that noise is really important. And in our field, we care about both of these, and that'll be part of the work. Sorry, I'm getting an occasional email, which I try to turn off. And so the signal-to-noise ratio that we measure, which one that we use, depends on several factors. What are we trying to measure? Are we comparing means? Well, that's almost always going to be a t-statistic, the most common of these. Or we're looking at variance, it may be a chi-squared. Or we're looking at the joint significance, which may be an f-statistic. The other thing that would determine what type of variable we use is the distribution of the data. Is it a binomial data distribution? Is it yes or no to an answer, or are people male or female? Those are binomial distributions. And then, or a normal distribution, which would be a bell curve, or a logistic distribution, which might be a flattened bell curve, or a Poisson distribution, which may be a count variable. Like the number of times that you go to a bar in a month would be estimated using a Poisson distribution because it's a count 0, 1, 2, 3, 4, whatever. And so there are hundreds of these distributional characteristics that you can use. Mostly you use either a t-statistic or a z or a modified z-statistic in these areas. And so you're going to learn about chi-squared and z-statistics and t-statistics and f-statistics, and that's going to be confusing. You're going to have to know when to apply them in the later classes. Just remember, it's all signal to noise. It's a signal to noise ratio. So the higher the signal to noise ratio, the higher the variables, the better they are. The lower the signal to noise, the worse they are. So that ratio of signal divided by noise, in a t-statistics, you're kind of looking for 2, and we've talked about that. But all of these test statistics are just simply measuring how much of what we know to be true is true, based on the randomness or the the variation in the observed data or relationship around it. And that's really comes down to a big point is that signal to noise ratio. So when you're struggling in managerial economics to determine when to use a t statistics or a chi-squared or a f statistic or a z statistic, just remember they're all measuring some version of the same thing. You got to know which one is important, but it's still the same thing. And the problem with what we've done in this area so far is that in much of the real world, we don't just care about comparing one item to a group. Now that works in some important applications. If we're filling bags of cereal, we want every bag of cereal to be indistinguishable from every other bag of cereal because we're selling it for the same price in a grocery store. So if there's a lot of variation in there, we're going to feel cheated, right? So we want to have people who are testing it really closely. Or if light bulbs fail or pretty random, we're going to get mad, right? And so that when we're doing quality control, we are going to be comparing just one thing or two things, a small number of things against a distribution of a population. But in more complex questions, we care about more than one variable. If we care about just two variables, and a variable in this case could be a characteristic. Typically, that's what we're talking about in business or social sciences. And here I pulled an example from psychology. If we're looking at one sample of 500 people and comparing to the characteristics of these people, to compare within them, we're comparing two variables. This is a graphical display of that. We can almost always compare these two variables. And here it's interpersonal avoidance and self-esteem, right? And so we're looking to see whether or not there's some correlation between interpersonal avoidance and self-esteem. And so those are two variables of people. We could look at height and weight. We could look at age and marital status. Because it doesn't have to be two random variables. It could be a discrete variable like gender, right, or marital status. At least I'm assuming here gender is a bivariate distribution, typically treated that way. But let's just say marriage. Either you have been married or you're not married, and you look at age, and you can see if there's a correlation there. In this case, there are two variables that are on a range: interpersonal avoidance between 0 and 5 here, and self-esteem between 1.5 and 4.5. And so here we fit a line that best fits the data. And that line fitting the data will tell us whether or not there's if the line has a lot of signal to noise ratio of over 2, then there's a correlation. If it's less than 2, or in this case typically if you got a 500 observations about 1.6, there's not. And so there are critical values that tell you this, but the strength of that relationship is important. If the signal to noise ratio is low enough, we say there's no correlation, there's no meaningful correlation here. There may be a measured correlation, but we don't think it's strong enough to be meaningful. And that strength can either come from the slope of this line here, how acute is this slope, right, or the spread of the variables around it. And that's a more artistic consideration, or more outside of simply the statistical analysis. If you have a really strong, an example might be, let's say I'm developing a vaccine for COVID, and there's a very weak correlation between taking the COVID test and people dying, right? It's very weak. Let's say it doesn't meet the 10% threshold. Let's say it's a 0.12. So that's outside what most statisticians would say is statistically relevant. But wow, if there's any correlation at all, that has a profound, very, very profound complicating factor in terms of policy. Because if there's a belief that people die of it, from it, and it's not statistically, if it's just outside statistically significant context, that's still going to cause a lot of people not to take the COVID vaccine. So the vaccine may not do any good. It may just cause people to die while the vast majority of people don't take it. So that's a case where you would care less about statistical significance and more about the cost. In the other extreme, what if you had you were producing drink straws out of plastic, and there was a tiny, tiny variance in the length of the plastic straw. Let's say it was 1.7 millimeters in the average length of these straws that they bundle in by the millions at McDonald's. But that difference between one manufacturer and another manufacturer was, there's statistically significant at the 1% level. In the million straws, there's a 1.7 millimeter difference between one manufacturer and another. Yeah, is that important? Right? You might be able to detect it statistically, but it may not be big enough to matter. I mean, certainly the eye is not going to be able to easily detect a 1.7 millimeter variation, and that's just the average. It may be that the average variation between the two samples is, a fraction of the overall the difference within the samples. Another way to think about it is schools, right? Let's say I'm comparing two high schools, and one high school has they're both 1,000 students in it. And we're trying to determine of these two high schools which one's better academically. And which one should I send my kid to, right? And so I'm choosing two different homes. Let's say there's a 4-point difference that is statistically difference between the average SAT scores in the two schools. Should that worry me an awful lot? And the only information I have is there's two schools there. I don't know, anything else about that school. Do they have an SAT prep class? Is one school filled with a lot of young teachers because it's poorly managed and so they're not as good? Or are there more poor people in one school who tend to do poorer on these placement exams? And if that's the case, then that little bitty difference may not matter, because the variance within the schools, I mean, is going to be a lot higher than the variance between schools. And so the range of SAT scores in both schools are going to be, tens of orders of magnitude higher, several hundred points difference in each school than the mean distance difference between the two of them. And so these are all examples where you're making some non-scientific judgment about the significance of a variable, and that's really comes with practice and reading. But even this two variable stuff, this doesn't do it for us really, right? It's not very complex. It doesn't tell us what we want to know. In most of the circumstances that we're going to be doing work in, we care about two variable comparisons, right? They matter, like the gender wage gap. So men make more on average than women. But to do anything about it, right, the really interesting information comes when we compare several variables at the same time, and that's called multivariate analysis. And multivariate analysis, usually it tries to tease out the contribution of each variable at the margin, the incremental contribution of each variable to some other variable. So and let's say we're going to analyze the gender wage gap, we obviously want to gather data on wages and gender. But is that all we care about if we're trying to measure a gap? No, because women might be educated differently than men, so we would want to, and that would affect wages. So we would care about education. We would care about the number of years of education and the major of the education. We would care about the job tenure. Women tend to exit and enter the labor force more frequently than men because of childbirth, and so that could reduce wages for women. We care about the occupation, right? If you have two people with the same level of education and one enters an occupation that pays less, that could, on a higher frequency, that would affect wages. We care about the age. Maybe the gender wage gap was really big 30, 40, 50 years ago, but has shrank so that workers in their 60s today may still experience it, by workers in their 20s may not. And then other characteristics might matter as well. What part of the country are they from? Is race involved? Does whether or not you're married have an effect? And so when you read the gender wage gap literature, when you really read the science to it, that academic journal or a well-researched long-form journalism piece, you're going to hear about all these things. And of course, there's a policy interpretation here. So the policy interpretation you often hear is, oh, there's a 25% gender wage gap. Women need to be paid more relative to men. Well, there's no legal mechanism, probably no constitutional mechanism to do that. And even equal pay laws for occupations don't work. I mean, you can't compare school teachers and police officers. Police officers get paid more, and because there's a higher risk of being killed than there is being a teacher, and so there's no really easy way to compare them. But then you would want to do the other analysis. Does education matter, or does occupation more often matter? If those are the cases, you can introduce policy remedies. You can introduce more children to different occupations, so more men are aware that they could be school teachers or nurses, and more women are aware that they could be infantry officers or firefighters, and that's a policy that could be introduced through schools or through something else that would expose more people to different careers so that those go away. And again, the goal of multivariate analysis is to measure the relative contribution of each. So if you measure all these together, you can say which is more important. Is it gender or education or occupation or age, right? And then if you're trying to reduce the gender wage gap, you would go to those areas. So and many policies inform this, right? There are many places that if require a man to take, if in a married couple, if the woman takes paid maternity leave, they force the man to do so. And the reason is that it wouldn't be fair if only women are taking, a 6-month paid maternity leave. That would give men an advantage in, say, academia, where in your 20s you're usually struggling to publish papers and make a name for yourself. If a woman gave birth to 2 children in 5 years, that's 20% of that career could be gone for childbirth. And let's say her another colleague or her husband who was married wouldn't give up that extra year over 5 years, so he's gaining 20%. So that there are policies meant to target that, and those policies come from the research that's done like this. And then just to end it all here, deciding which variables to include is the science problem, or economics or sociology or marketing. So which variables would explain a gender wage gap? We just don't randomly pick things out there. We know that education, job tenure, occupation, age, and other characteristics affect wage, so we care about that. And deciding what variables to include is what you're going to do the rest of this class, the next chapter after the test, and then the rest of this class and others. And that's only part of the problem. Evaluating the signal to noise ratio, that's the statistical sciences part. So typically people who are economists or sociologists are very well versed in that statistical science part, and part of that is also a combination to create real causal models, not just associations. And that's part of that. And then interpreting these requires both skills. If you don't have both the statistical science and the theoretical understanding of what's going on to build the model, you really can't explain that. And that's really all we are. I've talked about in the early chapters distribution theory, and I talked about univariate analysis, and I talked about different signal to noise ratios. We talked about comparing means and variances. Then I talked to you a little bit about the basic bivariate analysis with the line here. And then I talked about how the variance around the line here is the way we measure the t-statistic. And then I taught an economics class, and we did some modeling after that. And after this test and this material, we'll do some more modeling and this is called modeling, the statistical work that we're doing here. And so what I'm trying to do is to prepare you for classes where you're going to go deeply into the weeds on this material. And I'm trying to get you to see the forest for the trees, and have done this in enough occasions here in this class that you're not completely without any understanding of the material. So with that, I'll stop here. The next lecture will be reviewing the practice exam. Thank you.